Tutorial 10, Plastic Theory. Example 1. In example 1, we are going to use a bound theorem to estimate the collapse load of these two span beams. I think in the lecture notes we have some other example, right? Continuous beam. I believe that you can handle one span beam without any difficulty. In the notes, I actually give you all the scenario for one span beam, okay, in the lecture notes topic 11. So for continuous beam here, we have two span AB, span BC, under two different loadings, F1, F2. In this problem, you are asked to find out the collapse load, how large the load is required to make the structure collapse. So according to the introduction in the notes for continuous beam, you can consider span by span. You may assume that they have freely occurred on span AB, and then find out the collapse mechanisms. And then you can jump to another span, try to consider span BC. So for continuous beam, the calculation just based on span by span concept. Say for example, when span AB collapse, how many plastic hinges will form? Span AB is N span. N span, there is one real roller support at point A. Point A is already a real hinge, okay, free to rotate. So there's no plastic hinge formed at point A because point A is already a hinge. Point B, one hinge will form at point B, right? And then one hinge will form at the loading of the point node. After formation of two plastic hinges, you can start to see this kind of unstable Phillips mechanism, something like V shapes. So when you consider N span, there are only two plastic hinges formed at the N span. When you consider the second span next to the fixed end, this time, again, you need to find out how many plastic hinges and where are they. For fixed end, I think we have considered in our lectures already. For this portion, one hinge will form at the fixed end, right? And then one hinge will form at the roller support, at the middle, interior support. One hinge will probably form at the loading. So after formation of three plastic hinges, you can also start to see this kind of unstable mechanisms. So you can see that for N span collapse, two plastic hinges form. When the right hand side collapse, then it's required three plastic hinges. So here are the failure mechanisms we can firstly consider. And then for each mechanism, you apply our virtual work equation, our Ratan equation, try to equate the external work to our internal work, and then solve it. Mechanism 1, we consider the first span on the left. As mentioned before, when span AB collapse, there are only two plastic hinges formed. One is at the point node, one is at the interior support here. And then you have two plastic hinges. Suppose each of them under rotation feeder. You can see that this triangle is symmetrical. This triangle is symmetrical, has the same length here. So the angle should be the same. One side feeder, the other side is also feeder. Okay, there's no need to set some extra relationship. This one, relatively easy. And then based on the failure configurations, the first plastic hinge at the point node, the rotation, maybe I give them some name. This is A, this is B, maybe this is point C. Okay, the plastic hinge at point C is under rotation 2 feeder from geometry. This is feeder, this is feeder. So the angle outside the triangle is equal to 2 feeder. The rotation at point C is equal to 2 feeder. The rotation at point B is equal to feeder. Point A is not plastic hinge, so there's no contribution in the virtual work. This is the plastic work. Easy. And then the right hand side is the external work. External work, by definition, external work is equal to force times the corresponding displacement delta. What to find out delta? You can use the idea of arc length. Arc length tells you that radius times the rotation give you approximately the displacement. From this picture, you can see that the radius is equal to the length, right? L/4. Rotation is theta. So theta times the length L/4 give you the displacement delta. Delta equal to L/4 times theta. So you see theta on both sides. You can eliminate theta and then slightly rearrange the formula. You can get the first collapse load, 12 MP over air. For mechanism 2, you just repeat the same thing. Okay, I think this method is quite consistent. You just consider the failure mechanism and then use the virtual equation right here, and then eliminate angle on both sides. For mechanism 2, there are three plastic hinges formed. At point B, maybe I give them some name. Maybe this is point B, this is point C, this is point D. There are totally three plastic hinges formed. And then set up the energy equation. The plastic rotation at point B is theta. The plastic rotation at point C is also theta. The plastic rotation at point D equal to 2 theta. So you can see the total rotation is equal to 4 theta. When you're familiar with the calculation, I think you can immediately put down the total rotation, right? 4 theta. 4 theta times MP give you the total plastic work. Okay. When you get familiar with this method, I think you can immediately put down the total rotation. Theta plus 2 theta give you 4 theta. That is the plastic work. The right hand side is our external work done. I believe that the calculation remains the same. You can use arc length. You can use arc length to calculate the displacement delta. Same as case 1 actually. Same as case 1. So this time force 2, when second span collapse, the required force is 16 MP over air. We have two values. 12 MP and then 16 MP. We pick the smallest value as our collapse load of the whole structures. Because when both the loading increase gradually from 0, the structure will firstly collapse due to the smallest value. Okay, continuous beam. The tips of doing continuous beam is to consider failure on each span separately. Relatively easy. I think each mechanism only takes you around 1 minute per SMO for your calculation. If you're familiar with the method, I believe that each mechanism only takes you around 1 minute for your calculations. So it's relatively straightforward for this part. Example 2. Example 2, we consider rectangular frame structures. This time we have rectangular frames under two loadings. In this example 2, I assume that both loading are the same values, W, but they are in different directions, one vertical, one horizontal. Okay, I assume that the values are the same, but they're applied along different directions, applied at different positions. In these questions, we also use upper-bound theorem again to calculate the collapse law. Maybe I give you 1 minute. You may think about the column mechanisms of these structures. If you want to solve this problem, I think you have to understand how to predict the failure mechanisms. Otherwise, you cannot set up the energy equations and cannot solve the problems. If I give you 1 minute, you can think about what failure mechanism should be considered. Later on, we will go to discussion altogether. Okay, well, I believe that most of you have some idea about the failure mechanisms. When you're playing with this kind of rectangular frame, we have 3 kinds of failure mechanisms: beam mechanism, sway mechanism, and combine mechanism. Right? You may try beam mechanism first. I believe that beam mechanism is normally more easy, just like beam. And then once you have finished beam mechanism, you may go to sway mechanism. Sway mechanism means you have plastic hinge form at column ends, top and bottom. And then the structure becomes unstable if there is sway mechanism. You can see that it's free to move horizontally when the load increases slightly. Finally, you may consider combiner mechanism. Combiner mechanism means some hinges form at the mid-span at the point node, some hinges form at column ends. Here, I'll just give you one example. Okay. So when you answer these kind of problems, you just need to try a few scenarios. Normally, I will tell you how many you have to consider. And then, solve it, right? Set up the energy equation for each scenario, and then follow the minimum values. Let's go to the solution together. Mechanism 1, I try our beam mechanism. And you can see that for beam mechanism, it's just like a fixed end beam, to be honest. For fixed end beam, I believe that all of you should know how to deal with this problem. We have beam mechanism. 2 plastic hinges form at the beam ends, 1 form at the middle of the beam. And again, the loading is acting at the middle. So we have 2 equal angles. One is theta, one is theta. The middle hinge is under rotation 2 theta. I've explained many times. So when you set the energy equations, again, the theta plus 2 theta, the total rotation is equal to 4 theta. 4 theta times the plastic moment give you the collapse law. Give you the plastic work. And then multiply and then set this equal to the external work done. External work done can be calculated using arc length. You draw a circle, draw imaginary circle here. You can see the radius is equal to 2 meters and the rotation is equal to theta. 2 times theta give you delta. Okay, delta 2 theta. Force, diamond force W times delta give you the external work. In this case, you can see that there is no horizontal displacement. If there is no horizontal displacement, then you can ignore the horizontal force because there is no work done for the horizontal force. And therefore, you express all the angles using one single unit, so you can eliminate them easily on both sides of the equations. And then slightly rearrange the equation, you will have the collapse law. For case 1, to make the structures under beam mechanism failure, then the required load is equal to 2 times the plastic moment. But this is not the final answer. You have to also go through the remaining failure mechanisms. Mechanism 2, I try sway mechanism. And for sway mechanism, we have plastic hinges formed at column ends, just like here. And one side is under displacement delta. Now, normally, we make one assumption in our calculations. We assume that the beam remains actually rigid. So when one side displacement is delta, the other side is also under delta. Same translational movements at the top level. And based on this picture, you can see that if one side is under rotation alpha, the rotation on the other side should have different values if they have the same displacement. Here, I just arbitrarily assume that one is alpha, one is beta. One is beta. They are not equal. So if you set up the right equation, then you will see alpha, beta in the same equation. You can't solve it, right? If the equation having more than one rotation angles. As discussed before, the tips here is that you can find out some common displacement. Say, for example, delta. And I call this delta H. H stands for horizontal. Okay, H stands for horizontal. You can see that the horizontal displacement can be expressed using alpha and beta. This will help you to find out the relationship between alpha and beta. Say, for example, when you express delta in terms of the left-hand side column, the left-hand side column, you can use arc length theory. Right? This arc length. You can use arc length theory to calculate the displacement, which is equal to the height of the structure times the rotation. Similarly, you can express delta in terms of the right-hand side column. The values become 2 times theta. They are equal. They are talking about the same values, delta H. So this equation gives you some extra information between the 2 angles. 2 alpha equal to theta, or alpha equal to 1/2 theta, depends on which one you would like to use in your calculations. So right here, you can set up the energy equation again. To set up the energy equations, maybe I give them some name, A, B, C, D. Just help me to explain the position easily. Point A, the plastic hinge at point A. You can see that the plastic rotation at point A is only equal to alpha. Then what is the plastic rotation at point B? Now you can understand in this way. Point B, the plastic hinge at point B is connecting 2 members, the beam and the column. You can see that the beam has no any rotation. Right? The beam sides have no any rotation. The column side is under rotation alpha. So the total rotation at point B is equal to alpha. Okay, I circle the total rotation at different plastic hinges. Point D, I go to point D first. I think point D is more easy. Point D is at the ground level. This one, the rotation at point D is equal to theta. I think this one is pretty straightforward. Point C, finally. Point C, the idea of point C is quite similar to point B. Point C is connecting 2 members, beam and column. The beam remains horizontal, no any rotation. While the column is under rotation theta. So what is the total rotation at point C? The total plastic rotation is equal to theta, right? Only one side. So what is the total rotation in the whole structures? Alpha plus theta plus theta, right? 2 alpha plus 2 theta. Highlight the wrong one. 2 alpha plus 2 theta. And then time plastic moment, that will give you the plastic work. So to set out the energy equation is quite easy. You just calculate, you just count the total plastic rotations and then multiply by MP. That becomes your plastic work. Because MP normally is the same for all the second. That's our assumptions. And then the left-hand side is our work done. Work done is equal to the force times delta. From the picture, you can see that there is no any downward displacement. There's no any downward displacement. So in case 2, in mechanism 2, you can ignore downward force. Just consider horizontal force. The horizontal force is W. W times delta H give you external work. For delta H, you may use alpha, you may use theta, depends on which one you would like to use. Finally, you can use the relationship at the top to transform all the angles into either alpha or theta, and then you can eliminate them on both sides of the equations. After that, you can find that the collective load is equal to 1.5 MP, 3 over 2 MP, 1.5. Mechanism 2. So if you find that there are more than one plastic rotation angles, don't worry, just try to find out those common displacement and then express those common displacement using all the angles. It will help you to set this kind of relationship. The last one, I also believe that this is the most difficult one, combined mechanism. This is the failure configurations I consider in mechanism 3. 1 hinge is formed on the left, 2 hinges form on the right column, and 1 form at the middle of beam. Similarly, if I set some rotation angle, say for example, this one, alpha. You can see that in the picture, you can see the top left-hand corner has no any plastic hinge. The top left-hand corner has no plastic hinge. So this right angle remain right angle. Okay, this right angle remain right angle under deformations because there's no any plastic rotation at this corner on the top left-hand corner. So based on this property, 90 degree here. Then what is the horizontal? What is the angle over here? Alpha, right? Alpha. Same as the bottom angle. Then what is the angle on the other side? Alpha. Similar triangle, right? The triangle has the same length, 2 meters on the left, 2 meters on the right. So using similar triangle, you get the same rotation, alpha, on the right hand side. The rotation at the bottom on the right hand column is equal to theta. For sure, this is another value because assume that this is delta, delta H. The other side is also equal to delta H because assume that the beam is actually rigid. If they have the same displacement, then the column has the same length. So the conclusion is that they should have the 2 different rotation angles. One is alpha, one is beta. One is theta, just like the previous scenario, actually. So this angle, I simply let is equal to theta and other symbol. Then this angle, the angle below the top right hand plastic hinge is equal to theta. You can put down this kind of angle on your picture, okay? So how to solve this problem, case 3? Well, just repeat the same thing. Because in your problem, there are 2 angles. So you have to firstly find out those relationships between all angles. You can use the same common displacement delta H to find out the relationship. So this one I think is same as mechanism 2, no difference. Alpha, 2 alpha is equal to theta. You can use the top displacement, delta H, as the common displacement. It will give you the same relationship. Once you have the relationship, you can start to set up the energy equations. But this time you have more complicated equations involved. Talk about the plastic work first. Before showing you the plastic work, here I give you one more terms. The total rotation for the middle plastic hinge is 2 theta, right? So we can count the total rotation together. I give them some name: point A, point B, point C, and point D. A, B, C, D. At point A, the plastic rotation is equal to alpha. Okay, at point A, the plastic rotation is alpha. At point D, the plastic rotation is theta. I think these 2 are easy, right, at ground level. Then what about point B? Point B at the middle of the beam. Point B. You can see that point B is connecting 2 members, 2 beams, right, on the left and the right. Each of them is under rotation alpha. So the total rotation at point B is equal to 2 alpha at point B. The left beam under rotation alpha, the right beam under rotation alpha, alpha plus alpha give you 2 alpha. Okay, point B. So the idea is quite simple. You just take a look on all the members connecting to the plastic hinge to see their rotations and then add it up together. Finally, at point C, at the top right hand corner, point C. Point C, from the picture, you can see that point C is joining a beam and a column. The beam is under rotation alpha. The column is under rotation theta. So the total rotation at point C is equal to alpha plus theta. So you can mark the rotation on each plastic hinge on the picture. Then you can see that the first term in the solution, the first term actually represents point A, the second term represents point B, the third term represents point C, and then point D. 4 plastic hinges, you have 4 terms for your plastic work, ABCD. About external work is equal to force times displacement. Unfortunately, this time you can see that you have horizontal displacement and you have vertical displacement. So you have to consider both works, both forces. Delta W, horizontal force times delta H, give you the first work done. Vertical force times delta, I call it delta V, V for vertical. V for vertical, okay, H for horizontal. Vertical force times vertical displacement give you the second work done. Delta H and delta V. How to find out delta H? Mechanism 2, we consider already, right? How to find out delta V? Delta V is the value that we obtain in mechanism 1, right? Delta V. You can go back to mechanism 1 to see how to find out the vertical displacement at the middle of the beam. Here. This one, right? Exactly the same, delta V. So you can actually copy some answer from the previous mechanisms. We have alpha, we have theta in the equations. Try your best to utilize the relationship at the top to rearrange all angles into one single symbol so that you can eliminate them on both sides of the equations. Otherwise, you can't solve it. After that, we found that the W value is equal to 4 over 3 MP. Approximately equal to 1.333 something, right? 1.33 MP. Now we can compare the values for all three mechanisms. Mechanism 1 is 2 MP, something like that, right? Mechanism 2, I remember it's equal to 1.5 something. Mechanism 3, 1.333. So among all three mechanisms, it seems that mechanism 3 gives you the minimum value. So the collapse load of these structures is equal to 1.33 MP. Okay, that's how you can deal with rectangular frames. Rectangular frames, basically, you just need to consider three mechanisms, four mechanisms, and combined mechanism. Try your best to solve the reservoir equation and solve it. These examples, example 3, we have structures with inclined members, and also we have unequal loadings. These are the two features in these problems. Please make sure that you know how to how to solve these kind of problems. And yes, you can see that for these structures we have fixed end at the bottoms, and we have for fixed end we have 3 reactions on each side. In total, we have 6 reactions. We have 6 reactions, and we have 3 equilibrium equations. The degree of indeterminacy of this structure is equal to 3. The degree of indeterminacy is equal to 3. If you still remember, in topic 11, topic 12, we have mentioned some simple relationship between degree of indeterminacy and the number of plastic hinge that can make the structure collapse. The number of plastic hinge that will make the structure collapse under a complete mechanism is equal to n plus 1. This is also the maximum number of plastic hinge that will form in the structures. So it seems that 4 plastic hinge will make the structure collapse. Say, for example, if plastic hinge form at point B, point C, point D, and point E, after formation of 4 plastic hinges, you can see that this part becomes totally flexible. When the loading increases slightly, you will expect to see back displacements occur. We don't want this occurred. That's why we call it collapse. And then the next thing is to estimate, to try your best to predict the collapse mechanisms. It seems that we have 5 corners: corner A, corner B, corner C, corner D, corner E. Normally, the bending moments are maximum at the member ends, right? Just like point A, point B, C, D, E. It seems that we have 5 critical points. We have 5 critical points, but 4 hinges is sufficient to make the structure collapse. So it seems that we have more than 1 collapse mechanisms. We have to try different combinations. Maybe B, C, D, E. Maybe A, B, D, E. We have to try different combinations and then find out the relationship between P and W. Okay, these are the way how to deal with this kind of structures, trying with inclined members. As usual, try all combinations. 5 critical positions, A, B, C, D, and then you can try any 4 combinations. Try any plastic hinges at either one of the positions. Well, in the solution, I consider several scenarios that you have some idea. Say, for example, mechanism 1. In mechanism 1, I assume that plastic hinges form at point B, point C, D, and E. Oh, B, C, D, E. This is the one that I showed you before. And what should we do after that? Firstly, put the plastic hinge on the structures and then try to sketch the movement, right? The possible movement. It will help you understand how it behaves. And you can see that basically this region is free to move after formation of 4 plastic hinges. So totally flexible. We don't want this happen. Mechanism 1, what should we do? We assume some plastic rotation angle. Say, for example, point B. At point B, we assume that the rotation is equal to theta. At point D, the rotation is equal to phi. At point E, the rotation is equal to alpha. Alpha, theta, phi. Point C is connecting member BC and member CD. And actually, the rotation for member BC and member CD has been described using theta and phi. So the rotation of point C depends on theta and phi. Don't need to set up one more angle. Okay, 3 angles. Then again, if you have more than 1 angles, theta, phi, alpha, then what should we do? According to the tips that I give you in the nationals, if you find that if there are more than 1 angles, then you just need to find out some common displacement. Use those common displacement, correlate different angles together. For this kind of frame with inclined member, there are 2 special displacements are really helpful to solve this problem. The first one is the vertical displacement at point C. Point C is here. The vertical displacement here. Maybe I call this delta CV. Displacement at point C along vertical direction, I simply call it delta CV. Delta CV, you can see delta CV can be expressed in terms of member BC or member CD. Okay, delta CV can be expressed using the left-hand side member or the right-hand side members. So that will help you to correlate the 2 angles, theta and phi. Now we are considering inclined member. For inclined member, how to find out downward displacement? The top picture shows you the tips. Actually, I extract from the lecture notes. If you consider inclined member with inclination angle alpha, this hinge is under rotation theta. If you want to find out the downward displacement, it seems that the calculation is simply equal to the horizontal distance A times the plus rotation beta. So if you express delta CV using member BC, the value is equal to 5 theta. Similarly, if you want to express delta CV using the right-hand side member CD, the value is equal to the distance, also equal to 5, fortunately, times the plus rotation phi. You can express delta CV using the same, using the 2 different angles. And this gives you the first relationship between theta and phi. The first critical point vertical displacement upon C give you some idea about the angle theta and phi. The second useful point is point D, the horizontal displacement at point D. That means here. Maybe I call this delta dh, displacement at point D along horizontal direction, delta dh. Delta dh, just like the previous concept, delta dh can be expressed using the member DE. I think this part is trivial because delta member DE is a vertical column. On the other hand, the horizontal displacement can be described using the combination of member BC and member CD because they meet at the same point D. Okay, so you can express using member DE or the combination of member BC plus member CD, and that will also help to correlate alpha, theta, and phi. Take a look for the member DE, the vertical member. The vertical member is not easy, just a vertical column. A vertical column, how to calculate a vertical column is horizontal displacement. This one just like the rectangular frame. The radius here, the height 5 meters times the plus rotation alpha, give you the horizontal displacement due to member DE. So when you reach a solution, 5 alpha actually represent the contribution of DE. I think this part is easy, but what about the contribution due to the combination of BC and CD? Let's consider BC first. When BC rotate, you have diameter displacement, and also you have horizontal displacement, right? So that when you combine them together, it becomes a diagonal path. How to find out the horizontal displacement of an inclined member? This time you can use the other expressions. If you want to know the horizontal displacement of inclined member, the value is equal to B, the vertical height, times the plus rotation theta again. The height of this inclined member is 2, the rotation is equal to theta. Okay, so the contribution of BC is equal to 2 theta. But that's not the end, because the upper part composed of two members, BC and CD. CD also rotate, contribute a little bit on the total horizontal displacement. Then what is the contribution of member CD? Member CD is also inclined member, okay? Also inclined member. To find out the contribution of inclined member, the equation just give you at the top. It is equal to the height of this member, 2 times the rotation. The rotation for member CD is equal to phi. 2 phi. 2 phi is the contribution of member CD. Add them up together, it becomes the total displacement at point D, right? BC move something, and then CD move a little bit. When you add them up together, it becomes delta DH. Should be the same as the 5 alpha, because you're talking about the same positions. So together with this relationship, you can now correlate theta, phi, and alpha. Okay, you can now correlate theta, phi, and alpha. And finally, you can express everything using one single angle. You can set up the energy equations. I eliminate those. I eliminate those irrelevant drawing to make the picture more clear. And this is delta dh. So what should we do now? Now we are going to set up our algebra equations because we now realize all the relationship between all angles. And you can see that again, I try to consider plastic work first. I believe that plastic work is more easy to obtain. And you just need to count the number of rotation. I mean the total plastic rotations for each hinge. Point B is connecting two members. Member AB, member BC. You can see that in this picture, member AB has no any movement. Right? Member AB remains straight. No any rotation takes place for member AB. Member BC is under rotation theta. So it seems that at point B, the rotation is equal to theta at point B. At point C is joining member BC and member CD. Member BC is under rotation theta. Member CD is under rotation phi. So the rotation at point C is equal to the rotation of member BC plus the rotation of member CD, which means theta plus phi. Point D, plastic hinge at point D is joining member CD and member DE. I think you understand the trick right here, right? Member plastic hinge D is joining CD and DE. CD is under rotation phi. DE is under rotation alpha. So the total rotation at point D is equal to phi plus alpha. Actually, you just need to look on the rotation of the adjacent members, then you have the rotation at the plastic hinge. Finally, point E is easy because point E is at the bottom. There's nothing below it. Out rotation. 4 plastic hinges, 4 terms. B, C, D, E. This is the plastic work. And then you have to calculate the external work. In this problem, you have vertical displacement, you have horizontal displacement. So you have to consider both forces, W and P. W times the diameter displacement, delta CV, plus the work done due to horizontal force, P times the horizontal displacement, delta DH. Delta CV and delta DH has been obtained already above, right? You have delta CV, you have delta DH. Just use the angle that you are familiar with. Finally, use the upper two relationships, transform all the angles into a single symbols so that you can eliminate things on both sides of the equation, something like that. After some simplification, my answer is that we have one interaction formula, 5W plus 4P equal to a value 5.6 MP. 5.6 MP. This is the first interaction formula between W and P. Then what is the meaning of this equation? The meaning of this equation is quite easy. Any combination of W and P that satisfy this equation will make the structure collapse under mechanism 1. Okay? Any combination of W and P fulfill this equation equal to 5.6P will make the structure collapse in this mechanism 1. That means plastic hinges form at B, C, D, E. Interaction formula. Case 2 is actually the most easiest one. Case 2, we assume that plastic hinge form at point A, point B, point D, and point E. A, B, D, E. Right, for this scenario, the top part, BCD. The top part, BCD. And you can see that the top part, BCD, has no any plastic hinge in between. Okay? Portion BCD has no any plastic hinge in between. That means it remains rigid in our calculations. If this part is rigid, so actually you can replace this rigid part using something like a horizontal member. The upper part BCD is rigid, so to make your calculation easy, you can replace this rigid part by a horizontal member. Okay, why I'm going to do so? Because after we arrange this, it becomes what? It's just like a frame, rectangular frame under sway mechanism. Okay, if you replace portion BCD using a rigid member, again horizontal, actually it is a sway mechanism of a rectangular frame. How to deal with sway mechanism? We have already discussed in the notes or in the previous examples. Sway mechanisms. If one side is under rotation theta, the upper part is also under rotation theta. The total rotations 4 theta times MP give you the positive work. All plastic hinge under rotation theta. Okay. For this one, we have no any for sway mechanism. We have no diameter displacement for sway mechanism. So you just need to consider the horizontal displacement. What is horizontal displacement? You can calculate easily. Delta H. Delta H is equal to 5 theta. Arc length. The radius is 5. The rotation is theta. 5 theta gives you delta H. So this one is easy. You can find our single values. Force equal to 0.8 MP. We make the structure under collapse mechanism. This is the second relationship we have for case 2. Case 2 actually is a sway mechanism, just like a rectangular frame. Case 3. Case 3, we assume that plastic hinges form at point A, point C, point D, and point E. A, C, D, E. As finally, consider these problems. For mechanism 3, actually the procedures are quite similar to mechanism 1. If one side is under rotation theta, the other side may have different rotation. I don't know, maybe phi, maybe beta, they have different rotation angle. If you find that they are not the same, then you can simply make different symbol for it. Right? One is theta, one is beta, one is phi. If you don't like the symbol, you may use the other. You may use ABC, you may use alpha, beta, gamma, up to you. Here I use theta, phi, and beta. Again, if you have more than one rotation angles, then you have to use some common displacement, find out their relationship. Actually, you need to consider the same things, the same positions. You find out the vertical displacement at point C. I call this delta CV again. We have two special points help you to correlate with 3 angles, delta CV and delta DH, right? Delta CV, the direct displacement can be expressed using the member on the left and the member on the right, CD. That's why it can help you to correlate theta and beta. There's one trick I want to give you here. Same as case 2, when you take a look on this picture, you can see that there's no any plastic hinge form in between A and C. Simply speaking, ABC, this part, portion ABC, remain elastic, right? Remain elastic. In our theory, plastic theory, we ignore all the elastic deformations. That's why portion ABC remain rigid, just like a single member. If you find that it is a single member, ABC is a single rigid member. So you can just like mechanism 2, you can replace this member ABC by using one single diagonal rigid member. This will help you to this can make the calculations easier. Why? If you treat this part as a single diagonal member, then how to find out the diameter displacement of a diagonal members? We explained already in mechanism 1. We have some shortcut, right? For diagonal member, under plastic rotation theta, the horizontal length is A, the vertical height is B. If you want to know the diameter displacement, the value of diameter displacement of a diagonal member is equal to A theta. So why I convert portion ABC to a single diagonal member? Because physically they're equivalent, they're rigid body, and it's also helpful to find out delta CV. If you express delta CV using portion ABC, the value is equal to the horizontal distance of this single diagonal member is equal to 5 meters. 5 times the rotation theta. So the first term actually is equal to the portion ABC. Okay, the tip is that you can convert the rigid body into one single strict member because it will not affect the performance. They are rigid. For diagonal member, you can evaluate diameter or horizontal displacement easily. And then you can use the right hand side to express delta CV. The right hand side portion in the member CD under rotation beta using the same equation A time rotation. Now the rotation is equal to beta. The value horizontal length is equal to 5. So 5 beta is the expression using the right hand side member. Again, you can find out the relationship between theta and beta. The second critical point is horizontal displacement at point D. I call this delta DH, consistent with my previous discussions. Delta DH. Well, as usual, for delta DH, it can be described using member DC, DE. Or you may express them using the combination of member CD and portion ABC. Delta DH can be expressed using DE or the combination of ABC and CD. Let's consider DE first. Member DE is a vertical member here, DE. And for vertical member, you can find out delta easily. The height here, the radius, 5 times the rotation 5, give you delta DH. And then you consider the left-hand side portion. There are two parts, right? ABC. ABC is equivalent to an inclined member. So you can find out the horizontal component. And then find out the contribution due to member D and member CD. Add up the two things together. It becomes the total displacement at point B. Okay. Find out the contribution for member A, for portion ABC, and then find out the contribution of member CD. Add them up together. The horizontal displacement for portion ABC. Again, you treat ABC as one diagonal member. The mode is the horizontal value for diagonal member. It is equal to the height of the diagonal member times the plus rotation at the plus hinge. For this diagonal member, this one, the height is equal to what? The height here is equal to 5 plus 2. That means 7. The height of ABC is equal to 7 Peter. The height of member CD is equal to 2. So when you write the solution, actually the first term is due to contribution of ABC. The second term is due to member CD. When you add them up together, it becomes the displacement at point D. Okay? And this equation helps you to correlate phi, theta, and beta, same as situation 1. You can correlate all angles together. So finally, you set up the work done equations and then solve it. You can count the total rotations. Say for example, point A. At point A, the total rotation is equal to theta. At point C, the total rotation is theta plus beta. Because point C is joining portion ABC and portion CD. ABC is under rotation theta, CD is under rotation beta. So point C is under total rotation theta plus beta. Point D, the total rotation at point D is equal to beta plus phi. And finally, at point E, phi. So when you write the solution, the first term is actually due to point A, and then point C, point D, and then point E. External work. External work, same as the previous one. W times delta CV plus P times delta DH give you the total external work due to horizontal force and vertical force. Slightly simplify the equation together with the relationship above. Then you can express everything into one single angle, rotation angles. You can eliminate angles and set up these energy equations. Again, any combination between W and P that satisfies this equation will make the structure collapse in this mechanism 3. Normally, we will present these 3 equations graphically in this way. We can present the previous 3 equations graphically. We call this interaction diagrams. Say, for example, the blue line represents mechanism 1, the orange line, mechanism 2, the gray line, mechanism 3. In this graph, I use W, the vertical force, at the vertical axis. The horizontal axis is the horizontal force P. I believe that you have no problem to plot in this graph. How to plot this graph? Say, for example, mechanism 1. 5W plus 4P equal to 5.6 MP. W is the vertical axis, P is the x-axis, equal to a constant. Okay, that means you just have to plot this kind of graph. X plus Y equal to constant. It's a straight line. Firstly, when you take a look on the equation, it's a straight line. How to plot a straight line? To plot a straight line, you just need 2 intercepts. You need the vertical intercept and horizontal intercept. Say, for example, you can net P equal to 0. Find out the Y intercept. Find the W intercept, and then you set W equal to 0. Find out the intercept at the horizontal axis. Okay, you find out the 2 ends, simply speaking. When P equals 0, find out the corresponding value of W, and then find out the P value, find out the P values when W equals 0. If you have 2 lines, if you have 2 points, join them together, it becomes your curve 1, line 1. Just redo the things 2 more times using XY intercept concept. Then you have 3 lines. What is the meaning of this graph? We mentioned a little bit in the notes. Any combination of PW within this area, then they're safe. No collapse, right? They're safe. If the combination reach the grid line, where's the grid line mean the combination PW satisfy equation 3. It will make the structure collapse in mechanism 3. Plastic hinge form at A, C, D, E, right? If the combination meets the blue line, that means it will collapse in mechanism 1, and so on. Outside the boundary, it seems not feasible because when the combination touches the curve, it already makes the structure collapse. So it seems that outside the boundary is not feasible. Okay, this is so-called interaction diagram, how to graphically present the influence of P and W with different failure modes. So this is the safe region, simply speaking. This is a safe region in the graph. It seems that the possibility to having splaying mechanism is quite little, right? Mechanism 2 just contribute a little bit. This leads to a vertical line. And most of the time it's contributed by 1 and 3, the blue and the grid lines. So this is how you can deal with structures with inclined members.